So let's now have a driven motion. So this time it's not free. We are now going to have an applied force G of t. So for a spring mass system, we will now be having a certain driving force. So in the spring mass system, there is this ceiling that moves in an up in a certain way. So it is either um, like an elevator wherein it would be pulling it up or pushing it down. So suppose we now take into consideration an external force F of t acting on the vibrating mass on a spring. For example, F of t could represent a driving force causing an oscillatory vertical motion of the support on of the spring. So like in the ceiling of the elevator. The inclusion of F of t in the formulation of the Newton's second law gives the differential equation of driven or forced motion. So MA is equal to negative kx minus beta dx over dt plus some function f of t. Dividing this equation by m, so we have second derivative of x with respect to t plus beta over m. So beta over m is twice of lambda dx over dt plus k over m, which is omega squared, equal to f of t over m. So that's capital F of t. So as in the preceding section, so we have beta over m is twice lambda and omega squared is equal to k over m. So we can solve this equation by variation of parameters or method of undetermined coefficients. So let us interpret this initial value problem. We have 1 over 5 d squared x over dt plus 1.2 dx over dt plus 2x equal to 5 cosine 40. So 1 over 5, so the mass is 1 over 5 units. 1 over 5 kilograms or 1 over 5 slugs. Um, the, the damping coefficient is 1.2. The spring constant is 2. And then the driving force is 5 cosine 40. With an initial condition, x of 0 is 1 half. So it was released 1 half units below the equilibrium position and it was just released. So no initial velocity is applied to the system. We can interpret the problem to represent a vibrational system consisting of a mass attached to a spring. The mass is initially released from rest, 1 half unit below the equilibrium position. The motion is damped with damping coefficient 1.2 and is being driven by an external periodic function with period pi over 2. So period is 2 pi over omega, so 2 pi over 4. So pi over 2. Beginning at t is equal to 0. Intuitively, we would expect that even with damping, the system would remain in motion until such time the forcing function was turned off, in which case the amplitude would diminish. However, the problem is given f of t equal to 5 cosine 40, which will remain on forever. So solving this, we first solve the homogeneous side of the equation. We multiply everything by 5. So we have um, y double prime plus 6y prime plus 10y equal to 0. So you have the solution to be equal to negative 3 plus or minus I. So it follows that your complementary solution would be e to the negative 3t plus times the quantity c1 cosine t plus c2 sine t. Using method of undetermined coefficient, so we can solve for the particular solution. So we have cosine 40, so a cosine 40 plus b sine 40. So differentiating it twice, and we're going to plug it into the equation x double prime plus 6x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 x 6 negative 6a plus 24b cosine 40 plus negative 24a minus 6b sine 40, and we're going to equate this to 5 times a cosine 40. So from the previous problem, we can see that this is equal to 5 cosine 40. Since we are multiplying it by 5, it would now be 25 cosine 40. So the resulting equation would now be, for cosine 40s, we have negative 6a plus 24b equal to 25. And for sine 40s, we have negative 24a minus 6b equal to 0. So b is equal to negative 4a, and plugging it in to the equation, we will be having a is equal to negative 25 over 102 and b equal to 50 over 51. So it follows that the equation would now be x of t equal to e to the negative 3t times C1 cosine t plus C2 sine t as your complementary solution. And for your particular solution, you have negative 25 over 102 cosine 40 plus 50 over 51 sine 40. When we set t equal to 0, the above equation, we obtain C1 is equal to 38 over 51. By differentiating the expression and setting t equal to 0, we find C2 equal to negative 86 over 51. So the resulting equation of motion would now be x of t equal to e to the negative 3t, and then we plug in C1 and C2, so that is 38 over 51 cosine t minus 86 over 51 sine t minus 25 over 102 cosine 40 plus 50 over 51 sine 40. So we have this what we call the transient and the steady state terms. So when f is a periodic function such as f of t equal to f sub 0 sine gamma t, or f of t is equal to fo cosine gamma t, the general solution for lambda greater than 0 is the sum of non-periodic function x of c of t and a periodic function x of p of t. Moreover, x sub c of t dies off as time increases. That is the limit of the complementary solution approach to 0. Thus, for large values of time, the displacements of the mass are closely approaching by a particular solution xp. The complementary function x sub c is said to be transient or transient solution, and the function xp, the part of the solution that remains after an interval of time, is the steady state term or the steady state solution. So note that, therefore, that the effect of the initial conditions on the spring mass system driven by F is transient. So the particular solution would give us um, a transient, the effect of the initial condition on the spring mass system by F is transient. So the one that gives um, a steady state response is the forced response, or the one due to the particular solution. So in the solution, e to the negative 3t times 38 over 51 cosine t minus 86 over 51 sine t is the transient, because take note that if this term approach infinity, it would become 0. So this would eventually become 0, while this one retains as t approach infinity. So it is a steady state term. The graphs of these two terms and the solution are given in the figures A and B respectively. So the steady state is the blue curve, and the transient is the pink that decays as t approach infinity. So it becomes 0. So like the case of um a damp sinusoidal term. So for example, for the initial value problem, d squared x over dt squared plus 2dx over dt plus 2x equal to 4 cosine t plus 2 sine t, with the initial condition x of 0 is equal to 0 and x prime of 0 is equal to x sub 1. Where x sub 1 is constant, this is given by x of t is equal to x1 minus 2 e to the negative t sine t plus 2 sine t. So the solution curve for these selected values of the initial value x1 are shown in the figure. So for various values of x, you can see that this initial condition, this initial velocity only applies for a transient time. But as t approach infinity, so this is the transient period, the small amount of time, and this is the steady state. So at t approach, as t goes big, as t approach infinity, the effect of the value x is negligible. Now, if there's no damping, so let us consider dE of a driven motion without damping. With the periodic impressed force and no damping force, there's no transient term in the solution of the problem. So also, we shall see that the periodic impressed function or force with a frequency near or the same as the frequency of a free undamped vibration can cause severe problem in an oscillatory mechanical system. So the one that causes the transient response is the e to the negative lambda t. So e to the negative lambda t cosine omega t plus sine omega t. So this one causes the transient response, the exponential term.